Hello and good evening. It's Thursday night. At 6 o'clock, we're starting class early. You'll certainly see this after 7. So I wanted to have class today in lieu of our meeting due to the weather to keep moving on the content. There's a lot of content in this class, and if we take and defer this entire lecture till Thursday, we're going to squeeze the back end when the material is more complex. So we need to keep moving. So we were going to move into today 12.9, absolute dependent motion, in our case, to particles. We will have a quiz on Thursday, by the way. We'll cut that out of this and add it then. So absolute means relative to a fixed frame, fixed reference frame, fixed axes. Dependent, that means there's a tying together of the particles with an inextensible cord. Basically, they're tied together with a fixed length of rope. It is not going to get longer, it doesn't stretch. So absolute dependent motion of two particles. So let's take a simple case drawn here of particle A and particle B. Now, the rope clearly comes up from particle A, goes over the pulley, and then down to B. What's shown here is what they call datum. Now the datums for these measurements, these displacement measurements, are a fixed reference point. They both come right back to this origin point here, and they're just straight off of that. So basically these distances are from the point at O to A and or to B. Now you see that the positive sense for these dimensions is away from the pulley. So they in fact point away from the origin if you look at them as a pair away from each other. And they are in the direction of motion of A and B. If A and B move, they're going to be along the plane or along the same direction as this measurement of the displacement A and B. You also notice a CD shown here in red. That little distance, that little bit of length of rope over the pulley will always be the same length, which is important because what we have here is we're going to use the property of fixed length of this rope to do some assessments of velocity and acceleration of these particles as a couple, and we're going to take advantage of the fact that the length doesn't change. So if we want to draw or write out the length of this rope, we can do this. We can say the length of the rope is going to be equal to SA. That goes from A up to the pulley, plus the length of CD, which goes over the pulley, and then the displacement of B from the pulley as well. So given that length, really, you can see if we take the time derivative now of that equation, the left-hand side is going to be 0. We're going to have a velocity of A plus a 0 because the length of CD is constant, and then a velocity of B. Rearranging, the velocity of A equals the opposite of the velocity of B, which makes sense. If A moves in the positive direction, then B must move in the negative direction because they're connected by the cable. Second time derivative, leaves that relationship for the acceleration. So there's a simple case showing you how the length, because it's constant, helps these equations be simplified. And we can also throw out areas of constant length. The rope segment, if you will be different over that pulley when those blocks move, but the length of that rope over the pulley will not be different. And so when we come to questions of motion, we can throw that out. So in effect, when you're dealing with pulleys and the length of this rope, we can really deal with these as a one-dimensional system. And so the integration relationship between speed and acceleration is quite easy to reckon. Let's take a more complex example. Here we have a system of 3 pulleys, 2 weights. So let's just walk through that. They're connected to a ceiling here. So I'm going to draw this, because this is a ceiling, makes a convenient point for a datum. So if I draw a datum right here, that's going to capture a measurement. Well, E doesn't move, that pulley's fixed. F doesn't move either. Even though there is a little bit of length of white rope there, that length will always be the same. So it's analogous to the rope going over a pulley. But so now we can measure the distance from here down to D. We'll call that SD. We can measure the distance down to C. Call that SC. Distance down to A, because it also will move, SA. Now again, you can see these are all going to be in the direction of motion. And there's really nothing else except SB, but I'm going to ignore that and just, I'm going to reckon SB is A. I'm just going to, well, D. I'm going to use D in lieu of B, and here's why. The distance from D to B is a length, and that length is going to be constant. So when I go through my time derivative, we're going to end up with this length dropping out. So to simplify matters, we'll just use SD, so we'll get rid of SB. All right, so let's write out that length equation. Now, how many length equations do we have? That's right, we have 2, because we have 2 ropes. So can't take this thing anywhere. So the length of the first one is going to be equal to, come down, no, I can't draw and do this at the same time. So I'll write it out and then I'll show you what I mean. So we have an SD that goes from F to D on the first rope all the way to the left. It rolls around pulley D up to C. Now that length is going to be SD minus SC. And then we're going to add to that the final length of rope, which is SA minus SC. So I'll show you how we got there. I'll walk through that. The first length is here, SD. And we go, and we're going to ignore, but we'll go around D, and we're going to ignore that length because it's always going to be constant. And the second length, SD minus SC, is this length right here, because it is SD minus SC. It leaves that length. Roll around the top. SA minus SC is this length here. So now we have that length plus that length plus that length, length of 1. Now I'm going to pretty this up, get rid of my scribbles. So now the second length, the second rope to deal with is the other one, which you see starts at B, comes up through D, around E, back to C. So length of 2 is going to start at B, which so we're going to use D for that, SD. We already talked about Y. And is this not working? 2 is going to be SD. So we're going to come up from D around E, and then we're just going to add that short length down to C, which is just SC. So there's length 2. So clearly, when we take the time derivative, let's do the second one. 0 is going to equal the velocity of D plus the velocity of C. And so, in the end, what I haven't told you yet is what we want to know. We know the velocity of A. Let's find the velocity of B. So velocity of A equals 4 feet per second. Notice it's positive because it's in the positive direction as reckoned by the definition of its distance. Going down is positive. And we want to know the velocity of B. So, which, as we've talked about, is in fact the velocity of D because they're linked together by a constant length rope. So velocity of, I'm just going to rearrange this equation so that we can substitute it later. Velocity of C equals the opposite of velocity of D. So now let's take the time derivative of the first equation. 0 velocity of D plus velocity of D minus velocity of C plus velocity of A, not the distance of A, velocity of C. Combining terms, we have 2 velocity of D's minus the velocity of C, 2 of them, and plus velocity of A. I'll substitute in velocity of C is the minus velocity of D. So 0 equals 2 velocity of D's minus 2 times minus velocity of D, where I substituted in, plus velocity of A. So 4 velocity of D equals velocity of A. Rearranging, the velocity of D equals the opposite of 1 over 4 velocity of A. Taking that up here, velocity of B is velocity of D, so velocity of B equals 1/4 on the negative of velocity of A. 1/4 of 4 is minus 1 foot per second. So we're showing B moving in the minus direction. Positive is defined as down, so B is going up at 1 foot per second. So it makes sense if A is pulling down, and this goes down, this goes up, pulls B up. Makes sense. So there you have it. Again, the trick was we marched along these ropes and made up these equations for the distances of the ropes, and we took the time derivative of each case. So let's do one more example, a little more complex yet. I don't have a Hibbler picture, so here's my ground. I have a 2-foot tall bench. On that bench, I have a motor. That motor is pulling on a rope. The rope is tied to a block, and we'll call that block A. And that motor is pulling at 1 foot per second. So there's 2 ways of doing this. But let's go back to our procedure, right? Well, what do we want to know? We've now defined this scenario. Tell me what the acceleration is of block A when its distance, and we need to define the distance still, is 2 feet. So, okay, so remember, we have to define the distance now in the direction of motion of A. So it would be inappropriate to call distance along the rope. We need to call distance along this track, and I'll do it from a datum. Since this is a fixed point over here, we'll call that our datum, and this will be our distance A. You said, but hey, we need to know the length of the rope so we can take the time derivative of it. So we have to use trigonometry to get there. But it's critical that we define this position in the direction of motion of the block so that when we take derivatives, we have the velocity of the block, not some crazy velocity of the rope that we then have to go trade to get out of. So look at this though. There's two ways of doing this. I'll show you my way, but first I'll talk Hibbler's way. What Hibbler wants to do is call your rope the distance from the block to some point, and then give that point a velocity and say the velocity of this point is 1 foot per second. That's what Hibbler wants to do. I don't like that because he's still inherently saying that the length of the rope is constant, and technically it is if you're talking this measurement, because that measurement just moves up, right? Until such point as you wrap that upper dot around the motor. So what I prefer to do, because I think it's more intuitive and it works, is I'll keep the length of the rope from the motor to the block, but then I'll reckon that the change in length of the rope is equal to that motor's wrapping speed. But since it's getting shorter, since it's wrapping, it's a minus 1 foot per second dl dt. So then when I take the time derivative of the length, once we determine it, then dl dt will be -1 instead of being 0. So let's get to it. So the length is just by Pythagoras, it's the square root, and I'm going to drop my units here, square root of 4 plus SA squared. This number squared, this number squared, square root gives us the hypotenuse. And so the time derivative of that, I'm going to rewrite this because it helps me use the chain rule, as 4 plus SA squared to the 1/2 power. So now the derivative is 1/2 of 4 plus SA squared to the -1/2 times the derivative of the inside, which is 2SA, times the derivative of the variable SA, which is VA. This is just dSA dt. Rearranging, and as you recall, dl dt is 1 minus 1. So these 2's cancel, and then rearranging, I have velocity. Basically, I need to move all of these terms to the other side. So I have a -1 over SA times the 4 plus SA squared to the 1/2. I could have written square root, but I'm going to go ahead and do in another second another time derivative to get to the acceleration. So I'm leaving it in the parenthetical terms to help me with the chain rule. So let's do that. So dVA over dt. Now, since the motor's running at a constant speed, that's going to be 0. Don't listen to me, because we're talking this number, not the length. If we were talking the length, then what I said is true. But if we're talking the displacement, then that's not true. So that's not 0. Anyway, let's do the chain rule. My first term, my second term. So derivative of the first term. Let me rewrite it once quick as well. I'm going to go just to help me, minus SA to the minus 1. Just write that term to make the calc easier. All right, so the derivative of the first term, minus 1 SA to the minus 2, multiply by the second term, minus, because I still have the minus, so I got to carry through, SA to the minus 1, so that's the left term. And now the derivative of the right, 1/2 of SA, 4 rather. 4 plus SA squared to the minus 1/2 times 2SA VA again. Now I'm getting a little bit close here, so let me draw those to separate it. So that's chain rule. Now some convenient things happen here. So the minus and the minus go away on here. So let me rewrite this as square root of 4 plus SA over SA squared minus, over here this SA cancels out with this 1 over SA. This 2 cancels out with this 1/2. So we left with VA over square root of 4 plus SA squared. I lost a VA. So when I took this first term, go back here, when I took the derivative of this one, I got this, but I don't have the derivative of the SA in there. So this needs to have a VA as well. So there's a VA term here. I screwed up my chain rule. All right, so carrying forward, let's pull the VA out. One over SA squared, square root of 4 plus SA minus 1 over square root of 4 plus SA. Now what's interesting here is VA, if we look up above here, VA is just minus 1 over SA times the square root of 4 plus SA squared. So if I take VA and I plug this in, I end up with minus 1 over SA times the square root of 4 plus SA times 1 over SA squared, square root 4 plus SA minus 1 over square root, nice, square root 4 plus SA. So when I multiply this term by this term, I end up with just 4 plus SA, and times this term, this whole thing, this whole second term becomes minus 1. So we're going to end up here with minus 1 over SA times 1 over SA squared times 4 plus SA squared minus 1. I'm out of room. So what I'm going to do is I'm going to grab this last term here. I'm going to take it with to the next slide. All right, so that equals, remember this was equal to the acceleration. Multiply the SA squared out inside that parentheses, 1 over SA times 4 over SA squared plus 1 minus 1 minus 1 over SA times 4 over SA squared plus minus 4 over SA cubed. And so that is, as you recall, the acceleration of A. It should be negative because SA is going to be getting shorter as that motor runs. It is. And so let's plug in. We're looking for the answer at SA equals to 2. So at SA equal to 2, we end up with minus 4/8 feet per second squared, or minus 1/2 feet per second squared. Now what's interesting, and what I like about this is, let's check our work. Let's go back into that. Remember the velocity equation right here. Let's grab it. This one. Come down here. Control V. Whoa. Did you see that? Oh, I did it again. So if we do the same thing and plug in 2 here, 1/2 of 4 plus 4 to the square root, right? So minus 1/2 times 2√2, or minus √2. And if you think about the motor, we were at 2 feet up, and the question was what happens at 2 feet out? And if this velocity is 1 foot per second, if we're at 45 degrees, then it makes perfect sense that we're at square root of 2 for the velocity of A going in this direction. Just a little bit of validation using trig that the answer makes sense. That was 12.9. So what we're going to do now is we're going to get into 12.10. Now 12.10 is when we get to do different things, so it's kind of exciting. What 12.10 is relative motion. Again, two particles with translating axes, with a translating axis, we'll say. So, translating, so I'll add in here, not rotating, because the an axis that's translating, you can also imagine if it was spinning. So we're only moving linearly with our translating axis. So let me just draw a very, very simple picture. If you imagine a helix, that this is in 3 dimensions, right? So I'm going forward and backwards with these loops, and that's just the sum of a circle. So I'm looking at a circle on the end and I'm going around it, but I only see it go up and down because I'm looking at the end, plus direction in right. So this is that's all it is. So what we're doing here is, when we talk about relative motion, we can reckon motion in one frame of reference and reckon motion in a second frame of reference, and then by superposition add them up and get the correct answer still. So fundamentally, we're talking about superposition of our frames of reference. So as we go through these problems, and we'll do a couple of them, we're going to have a translating frame, and then we're going to have a fixed frame. But it still holds true. We superimpose those on each other and have our correct answer. So, and to prove the point about superposition, what's the equation of a particle moving in a circle? It is the cosine of time it can be. I mean, there's different ways of doing this, but the cosine of time in the x direction plus the sine of time in the j direction gives you, in an xy sense, a circle. And then in the z direction, it's just time, some constant times time. In the k hat direction, I can add those three together clearly without making any laws of physics blow apart. So the math there validates that we can superimpose these. So, but what we end up having to do then is, okay, that was a pretty simple example, the helix, but how do we move between frames of reference? I'm going to pause here and grab a picture and come right back. Okay, so here when we're talking about a translating axis, we're talking about this point A. You can see my friend Billy standing on it. Billy's feet, they're flying to the right. Okay. Well, kind of flying upward to the right at 45 degrees. Anyway, so this whole axis is moving. All right. Billy's flying away. He's like magic. And so, but here's me, my eyeballs and Billy's eyeballs. So I'm over here looking at this point B out here on some curve somewhere. You know, Billy's doing it too, looking at it. You know, he sees a different direction. He sees a different angle on it. He sees it moving different relative to himself than I see it. And so all we have to do, though, to figure this out is take our positions relative to each other. So simplifying this back, let's put Billy in a stationary place. He's just sitting there. His position to me is this vector RA. So ignore his axis right now. And the second particle B is RB from me. And so I just have two position vectors defining that. Now, go to jump to Billy's frame of reference in the prime axes here. He's got a position vector, which we'll call RB with respect to A. We're going to talk about this nomenclature because it's easy to get backwards. So we'll talk about it for a minute. But that is the position vector of particle B relative to A or from A. So that's how I like to think about it. RB A. B with respect to A, or B from the viewpoint of A, is always RB minus RA. That's how we determine it. It's what I see as a position to R minus what I see as Billy's position. But so you see the order of these terms. B, B, A, RB with respect to A, RB from A. This order is important. If you swap R and B around, then you end up with the wrong answer. Effectively, you come in with this vector, which is A with respect to B, which would be wrong. So the other way to think about it is RBA. It's the first term is the point of the vector, the point of the vector, and the base of the vector is A. So you can see the point of the vector is here, and the base of the vector is there. So it's another way to think about it is when it's B with respect to A, the vector points to B, and its basis is A. So just don't lose track of that nomenclature. So we'll take this. I'll go here on the left. RB with respect to A. These are vectors now. Is the vector position vector to B from me now. This is absolute position minus the vector to A. And now if I take the time derivative of everything, I mean, by inspection, by definition, they all just turn into velocities. Because literally it's all time derivatives of positions. So they are all just vectors, and it is really that easy. So what this this velocity of b with respect to a now is the relative velocity, again, of b with respect to a. The reason that this was so easy going from here to here is because, here we are in Cartesian coordinate systems. RB is some RBX times I hat plus RBY J hat plus RBZ K hat, right? These unit vectors have no time derivative, so we don't have to use a product rule here. And when we translate an axis, up, down, left, right, our new position is still up, down, left, right. And so the k hat direction is still the k hat direction, the x direction or the I hat direction is still the I hat direction. And so these time derivatives go to 0, and I don't need to use a product rule. Translation. If I was rotating, that all falls apart, right? In Cartesian coordinates, because I can't have the up direction and the right direction if I, at a later point, I've rotated where up is now here and right is now here, then bam, I'm gone. I now have a time derivative of the unit vectors. So that's why we opened up the discussion here today with translating but not rotating. All right, so let's take an example. Again, I'm going to pause because I got a Hibbler picture. I'll be right back. Okay, so here's a relative motion problem. This is in fact 12.223 from the problem set in Hibbler. And obviously we're given velocities about A and velocities about B, and we need to find the velocity of A with respect to B. And secondly, that's number one. Number two, when will they be? What time is the distance between them? 600 meters. Okay. So let's go straight into the velocity equation that we just talked about. I need to insert a shape here. I'll block off part of this. Bear with me. So we'll take velocity. So velocity B with respect to A. So the velocity A with respect to B, right? So the end of the vector is going to be the A boat. The base of the vector will be the B boat. So we're going to try to figure out this, right? Well, the better way to draw it would be B is here, A is here. Those are the velocity vectors. So it's going to be something like that, give or take. Well, this is 10, this is 15. My drawing's probably not to scale, so don't trust it. But that's, in short, what we're trying to figure out. So velocity of A with respect to B is the velocity of A minus the velocity of B. And so just taking a look at this, we have velocity A is 10, and we've got 30 degrees going on here. So if we do, I'm going to do the x's and then I'm going to do I'll do them both. So minus 10, because this first term is the x term. So because I'm using 30 degrees here and not 120 degrees. So minus 10 sine of 30 times I hat plus 10 cosine of 30 j hat. That's velocity of A minus 15. I'm on the boat B, sine 45 Now the minus is because we're doing this relative term here. So if I thought the velocity had a negative term, I'd have to deal with it out here, but it doesn't, because the way we defined x's and y's, the positive is in the positive x direction, the positive y is in the up direction, and so I've got to take my recycling out. 15 times the cosine of 45 j hat. And so collecting like terms, minus 10 sine 30, minus 15 sine 45 I hat, minus 10 cosine 30 plus 15 cosine 45 j hat. Plugging and chugging, I end up with a 5 minus 10.61 in the I hat direction, and I did some sign magic on my notes here. How did I do that? Plus cosine. Right, this is a positive term here, and I turned it negative here, so this is plus, and then minus 15, that should be minus. So I pulled the sign out, is what I did here. These two terms became these two terms. Plus 8.66 minus 10.61 j hat. So we end up with a minus 15.61 I hat minus 1.95 j hat, or 15.73 at an angle of 7.12 degrees, reckoned this way, down from leftwards. So my picture up here was wrong. It was not to scale. This vector turns out to be short relative to this one, 10 to 15, so we end up with a slightly down and backwards vector via our math. So the relative velocity is 15.73 meters per second, almost going horizontally apart. So the picture doesn't really do justice if you consider it. So boat A clearly left earlier, if you look at the positions. All right, so the second half of the question was what is the time when they're 600 meters apart? So I'm trying to insert another blank space to write on here. It's a blank space. Oh, no fill is the wrong answer. White fill is the answer. Can't take me anywhere. This is why we can't have any nice things. There we go. This little one popped out of nowhere. All right, so really it comes down to if the magnitude of the relative velocity A to B is 15.73 meters per second, then I just want to know, and that's a constant. So really, how long does it take to get to 600 meters? I just divide that constant out. And right now you're thinking, you just lectured us last class about not doing this. But in this case, it works because the velocity, the average velocity is in fact 15.73. So you divide 600 by 15.73 and you end up with 38.1 seconds until they are 600 meters apart. pop this up. I had another example to do. 12.231, but is in fact exactly the same math and method that we just used. And so I'm going to skip it for now. If you want to read ahead, if you want a quick view of the quiz, here it is. Did you get that? So study that. Also, I posted on the Blackboard this equation sheet created by Hibbeler for the very purpose of this class. So it's ideal because it uses the same nomenclature and symbology that he does. And I will post, I've already scanned these in, so I'll post these as soon as I get this video up. I'll post my notes up as well. And with that, I will look forward to seeing you on Thursday. And I hope it doesn't take too long to dig out from the snow that we had for you all. Have a good night.